Okay, so here's the first Unit 1 Homework 1 video for you guys. I'm going to try to move through this fairly quickly, so there may be even some of the questions where I'll just write down the answer at the start, and that way if you know you've got it right, you can skip on to the next one. But let's get going here. So question 1, what is the quotient here, right? So 0.674 divided by 0.74 to the proper number of significant figures. Okay, so just a quick review of significant figures. Right, obviously any non-zero digit is significant, so we've got 1, 2, 3 up here, and then we have just 1, 2 down here. The zero that is leading, the zero that is in front of the numbers, does not count as a significant figure. So when we do our quotient, we're going to round it off to just 2 significant digits. You really don't even have to calculate anything if you just look at the options, right? This one has 3 digits, but we need to round it off at 2. This one has 4, but again we're rounding it off at 2. And this one only has 1 digit, so that's not the appropriate number. So my only answer that makes any sense is A for that first one. Okay, so make sure you're comfortable with the basics of significant figures. Question 2 obviously then is very similar to question 1. The reason that I threw this question in here is I want us to make sure we're thinking about pi in the appropriate term. So 8.104, obviously this would have 1, 2, 3, 4 significant figures. The 0 does count since it is between significant digits. So that would have 4. Pi, I know that sometimes we think of pi as 3.14, but keep in mind pi is not 3.14, right? Pi is 3.1415, and so on and so forth. So the important thing here is pi is never going to restrict the number of digits. So when I get my final answer for this, I'm going to round my final answer off to 4 significant figures because the 8.104. The pi is not going to affect the significant digits at all. So once again, just like the first question, really if I just look at my options, the only option that has 4 significant figures is option C. Okay, so obviously you can calculate that as well, but that's where we would round it off to 4 sig figs. Question 3 really just asks us to re-represent 400 nanometers in terms of centimeters. So you could do this as a straight shot. I would actually recommend doing it in 2 stages, and what I mean by that is I know that 1 nanometer is 10 to the negative 9th meters. So I would rewrite this as 400 times 10 to the negative 9th meters. But then I know that there are 100 centimeters in every nanometer here. So then I would take, if I'm converting from meters to centimeters, right? So if I'm thinking kind of the Monroe type thing, for every 1 meter, I'm actually going to multiply it by 100 centimeters. So I would get 400 times 10 to the negative 7th. When I multiply 400 times 10 to the negative 9th times 100, right, that just reduces the power up here by 2. And then obviously looking at my options, that's not one of my options because this isn't scientific notation yet, right? I need to move the decimal 2 points this way, and as I move it 2 points that way, this number is going to increase by 2. So I'm going to be 4 times 10 to the negative 5th centimeters. Okay, so again, just conversions, making sure you are pretty comfortable with conversions. You could have also right from the start maybe made this 4 times 10 to the negative 7th meters and then gone from there. But either case, you do need to be pretty comfortable converting. Another quick review then of conversions here. We want to take 4.50 kilometers per hour to the units of feet per minute, and they do give us the conversion ratios for meters to feet. Okay, so I'll set this one up in the traditional mole road fashion here. So it's kilometers per hour, right? So hopefully for most of this is review, but in case we need to see it again. If I want to go from kilometers, I'm first going to go to meters because I know the conversion from meters to feet, but I don't know directly from kilometers to feet. You could obviously try to think that through, but I'm going to go ahead and go through kilometers to meters. So I know for every 1 kilometer, right, kilo stands for 1,000. So for every 1 kilometer, I have 1,000 meters. So I've taken care of that, but I want to go on, right? I want to go from meters to feet. So for every 1 meter, there's 3.28 feet, which takes care of my meter unit here. So that leaves me with feet on top, which is what I want. Be careful here, we're so often used to going from hours to seconds that sometimes you might naturally write 1 over 3,600. But in this case, we want to go to minutes on bottom. So I want to end up with a minute on bottom, or minutes on bottom. And then I know that for every 1 hour, right, there are 60 minutes. Okay, so just setting this up and then solving it the rest of the way out. So at this point, all I do is I multiply across the top. So 4.5 times 1,000 times 3.28, and then I divide it by 60. So when I do that, I get about 246. So I end up with 246. Again, looking at my units that are left, I've got feet over minutes, which is what I wanted. So 246 feet per minute, which, hey, that's one of my options, so that's a good thing, right? Anyway, hopefully this makes sense. Again, if you have trouble with conversions, if you need to review this more, come find me, because it is very important we know how to convert our units throughout the year. This was actually, question 5 here was a concept we covered specifically in class. I did try to bring your attention to it when we looked at it, but it's a good concept to think about. So when can we be certain the average velocity of an object is always equal to the instantaneous velocity? Always, never, only when the velocity is constant, only when the acceleration is constant, only when the acceleration is changing at a constant rate. Well, if we think about this, right, if I'm thinking in terms of my velocity versus time graph, or actually let's even just think about my position versus time graph first. Right, if my position versus time graph was a curve, then to find my average velocity, I would find my change. So if I wanted to find my average velocity between maybe these 2 points, I'd find my change in x over my change in t. In other words, I'd find my slope between those 2 points. But that average velocity is definitely not the same as the instantaneous velocity at any moment in time, right, at any instant in time leading up to that. If you look at the slopes of each of these blue lines, each one of those is a little bit different, except maybe this guy down here, from the slope of that average. So we definitely can't say that it is always true, right? So we can rule that out. But there are instances where it will happen, and the most common one, the only one really, is if I go again to my position versus time. Well, what happens if I have a straight line? Well, if I have a straight line, then the average velocity between any 2 points is going to be the same as the slope of that line, which is also the slope of the line tangent to that line. So in this case, at any given point, the slope, which is the velocity, would always be the same as the average velocity. Okay, so the only time that we can ensure that the instantaneous and the average velocity will be equal is when the velocity is constant, or when the slope of my position versus time function is a constant. So again, velocity has to be constant, and then I can say that the average equals the instantaneous. And that is a very powerful conclusion, so it's something I want you guys to be comfortable with. Question 6 here is a pretty basic conversion from position versus time to velocity versus time based on their graphs, right? So the figure gives us a position versus time, and they ask which of these best describes the velocity versus time. Well, to interpret the velocity, right, we looked at this in the last problem. If I want to find the velocity from a position versus time graph, all I have to really identify is the fact that velocity equals a change in position over a change in time, or in other words, is the slope of my graph. So if I just kind of think this through from instant to instant, so initially the velocity, the slope of that graph is pretty steep, and it's a positive steepness, right? It's going up as we go from left to right. So that tells me that the velocity is initially a positive number. Well, that right there helps me eliminate A and B, because if I look at A and B and I'm looking at my actual velocity graph, this down here would be indicating that the velocity is negative. This down here would be indicating the velocity is negative. We know that the velocity, because of the slope, should be a positive quantity. It should be a positive number. And even C, I didn't even look over here yet, but C is already ruled out as well. So just from that first point, actually no, it has to be D. But let's look a little bit more as to why. So initially the slope is very steep in the positive direction. As we go further along this curve, it's still positive, but what's happening to the slope? Well, the slope is decreasing, right, and so on and so forth, until eventually over here the slope is almost zero. So that's what's happening, right? It's still positive the whole time. It's still going up as we go from left to right, but it's becoming a lesser and lesser positive value, which is why D is perfect for that. Now I know some of us are thinking, well, this is almost a parabola, and so how come it's not a straight line? But the fact of the matter is we don't know if this is a parabola, and in fact based on the curve it's probably not, because it's not giving us a straight line function. And again, we'll get more comfortable with that stuff as we go through. But good things to be thinking about if you were thinking in that degree. Okay, for question 7, we've got a cat running along a straight line on this x-axis here. It goes from point A to point B, so it goes all the way over B and then back to C. The distance between A and C is 5 meters. So I'm going to go ahead and start to label this a little bit. The distance between B and C is 15 meters. So obviously, 10 meters, I got ahead of myself. this is 10 meters. And then obviously that tells me that the entire distance right between A and B is 15 meters. That's what I was thinking. But anyway, and the direction, the positive direction on the x-axis is to the right. So we'll assume that going this way is positive and going this way is negative. Okay, so the time it takes to run from A to B is 20 seconds, and the time that it takes to run from B to C is 8 seconds. As the cat runs along the x-axis between points A and C, what is the magnitude of its average velocity and what is the average speed? Okay, so again, the motion of a cat here, he starts at A, he runs over here to B, and then he runs back to C. Very key concept, something we've seen a lot of if you had this last year, but even if you haven't, something hopefully you're getting pretty comfortable with. If I want to find the average velocity, and I am going to use the bar to represent the average velocity, I want to know my change in displacement over time, and it is very important we're talking displacement over time and not distance over time, right? During the entire trip, the total displacement is just 5 meters, right? And in this case, it's actually going to be a negative 5 meters to the left, since they've defined this as the negative direction. So it'd be negative 5 meters over the total time that it took for that to happen. So 20 seconds from A to B, and then additional 8 here from B to C. So a total time of 28 seconds. Okay, so this would actually be a negative 0.179 meters per second velocity. However, this question does specify it just wants the magnitude, so I actually don't need the negative sign. I actually would just want the 0.179 meters per second. And I do want you guys to start thinking about that and try to answer that question correctly. Don't include the negative if they're just asking us for the magnitude, because the negative is only indicating the direction. And magnitude and direction, right, are separate elements of my velocity. But in any case, hopefully part A wasn't too bad, right? I just needed to know the displacement over time. Part B for speed, again, the key concept here, if I'm ever looking for the average speed, I'm not looking for the displacement over time, but rather the total distance over time. Okay, so this time the path is very important. As the cat runs out and then back, the total distance that the cat goes is 15 meters from A to B, and then an additional 10 from B to C, so the total distance is 25 meters. There is no direction associated with that, so I'm not going to worry about positive or negative. And then I'm going to divide that again by the total time of 28. So I get about 0.893 meters per second for the average speed. And again, there's no direction associated with that. That doesn't have a direction, because speed is just a scalar quantity, and therefore it just has a magnitude to work with. Okay, so example 7 here, question 7, hopefully a very good one to illustrate the difference between average velocity and average speed, and to get us thinking about directions and magnitudes and things like that. So hopefully this one wasn't too bad. Okay, so I told you guys to save time, I would go ahead and write down the correct answer. So the correct answer for this is 100 meters, and we'll look at why. So if you feel confident with that, awesome, you can move on, but we'll try and look at why here in the remaining time in this part. Okay, so the easiest way to think about it is this. We know that one person starts over here, right? And then the other person starts over here 100 meters away. And then the dog is starting next to one of those individuals. So here's the dog, right? They're 100 meters away. As those two people walk closer together, we know that collectively they have to cover 100 meters. So if we can find the time that it takes for them to cover the 100 meters, we know that the dog was running at a constant rate the entire time. So if you just take then the dog's velocity, his constant velocity, times the time that it takes for them to meet, and you've got your answer. Okay, so the way that we can do that, if they're moving towards each other, we can set this up kind of like we saw in class. We know that Arthur is moving at 3.0 meters per second. If we take that times however long he was walking, we would know his distance. We know that Betty here is moving at 2.0 meters per second. Again, times her time would give us her distance. And we know that total, these two times need to add up to 100. Well, because it takes the same time for them to reach each other, I know that that means it's 5.0 meters per second times t equals 100, which tells me again that t equals 20 seconds. And finally, because I know that Spot here was running at a constant 5.0 meters per second for the entire time that it took them to reach, for the entire 20 seconds, that he had to have covered the 100 meters as well. Okay, so the fact that it's 100 meters is coincidence based on the fact that their velocities add it up